Good. That's a good answer. So thank you. Yeah. A few things. One, what a tremendous event. It's only really possible because you all also decided to attend and make it even better than we had planned. So thank you all for being here as attendees, as sponsors, as speakers, as volunteers. So there are many of you here. A few notable people that I want to thank. Kim Hunter, she came all the way from Cambridge and sits with the MIT Alumni Association. Kim, stand. Thank you, Kim. So Kim makes sure that alumni programs remain awesome for those of us that have left Cambridge, so thank you. And in addition, you've probably heard his name by now. Has anyone heard about Shuja? Raise your hand. Good, that's a good answer. For many reasons, one of which is he's taking over this job as club president soon. So you can direct questions to him. If you have questions and feedback. No, yeah. So yeah, we know everyone had an awesome experience. We also hope to make it better and better every year, so please be very open with us. You can email, actually, his team alias, tech@mitcnc.org, and we will incorporate all of it. So Shuja had probably dozens of volunteers supporting him, so thank you. Many of you are here in the audience. We appreciate you. So thank you for being here and thank you for supporting. Also, many sponsors. You may know that we are a nonprofit, so this is quite an expensive event to host. It would have been nearly impossible without our sponsors, so we'll just clap for them right now. Thank you. It occurred to me after a couple of minutes of speaking that I didn't tell you my name. So my name is Bridget Brett. I'm class of 2006 from MIT, so I'm no longer a young alum. But I think I still look pretty good, so. Thank you. All right. Okay, so we thanked a lot of people. There's also many board members here in the audience. Thank you for being here. We've had a history of amazing volunteers, so thank you for taking part. And also, we shared this a couple times, but one of the coolest pieces about this conference, I thought, this year was the gender parity that we were able to achieve. Raise your hand if that was noticeable. Oh, yeah. Awesome. We think so, too. Freaking awesome. Thank you, Shuja, for, yes. So I'd like to take credit for it because I am part of the parity, except for really Shuja led the way with that. So thank you all for participating in helping us achieve that goal of 50-50 or even greater female participation. Finally, I think it's important that we formally recognize Shuja. So we did get him a card. It also has a message of what the gift is that's going to come with it, but right now it's just a card. So Shuja, come on stage. So Shuja's class of 1999, also no longer young, but still looks good. And yeah, Shuja's just such a joy to work with. He and I have become friends. He calls me more than anyone else I know. So thank you, Shuja. Also, yeah, he's just an awesome visionary, super persistent, diligent, inspirational. Everything that matters is a leader. So I've learned from you. I like working with you. I need a little bit of a break. So come July 31st, I mentioned I'm going to have a party. I don't know where yet, but it's going to be a big party as I pass the torch to Shuja, since he's president-select for the club. Anyway, Shuja, tremendous job. Thank you. You outdo yourself every single year. You make it hard for anyone following you. Keep it up.
Thank you. It's been a team effort. Thanks.
Oh. Thank you.
This wouldn't have been possible without Bridget's support and sort of allowing us the free reins to go out and experiment and do this. And we started experimenting with the tech track about 2 years ago when Bridget took over as president. And for the last 2 years, we've done about 20 events, but it's not possible with one person. It's like over a dozen sort of volunteers, most notably Vivek, Arjun, who've been throughout this journey for the last 2 years, but then in addition to that, there are like so many other folks, and I just, like, but those two people have been there constant. But thank you so much for Bridget for your leadership and allowing us to do what we're doing.
Of course.
So,
thank you.
Sure.
Also, Arjun and Vivek will get you cards as well, don't worry. And finally, you may have attended the dinner last night and laughed a lot. Wendy Zheng, class of 2009, was part of the emceeing for that event. She's going to help introduce our closing keynote speaker. Thank you, Wendy.
All right, everyone. Well, first of all, I just want to say everyone looks fabulous and unartificially intelligent. So yesterday at dinner, we announced the awards of the AI Influencer Awards, and this morning Shuja mentioned them. One person was not at the dinner last night because we had issues with SF air traffic control. That's a joke. No. But if you want to find out, just ask anyone at the dinner and come to dinner next year. But today, SF air traffic control did work out, and so I'm very honored to present the Trailblazer Award to our, first of all, Trailblazer Award, what is that? This award recognizes an individual for their inspirational breakthrough, founding new fields of study, and launching new industries. And this year, we'd like to honor Dina Katabi, Professor Dina Katabi. Please come on up. And so she is the Andrew and Irma Viterbi Professor of EECS, that stands for Electrical Engineering and Computer Science, aka Course 6. For non-MIT here, if you say that, Course 6, everyone will be really impressed with you at MIT. And she's also the co-director of the MIT, or actually director of the MIT Center for Wireless Networks and Mobile Computing. And she's won tons of major awards, but I'm just going to only mention 3 of them. One is the MacArthur Fellowship for her work in 2013. Also, she became a fellow for the Association for Computing Machinery as well, so ACM. And in addition to that, in 2017, she was elected to the National Academy of Engineering. So very, very accomplished. She also just last week gave a TED Talk on stage on her wireless research, which is one of the many few areas of her wireless research, which is absolutely fascinating. So I encourage you to watch that as well when that comes out. But I did roast everyone a little bit yesterday, so I'm not going to let you escape that. Basically, the fun fact about Dina is that when she was, she grew up in Syria. Went to school there and was able to get the best scores in the first category. And apparently, I learned yesterday, if you go to school in Syria and you make the best grades, you're supposed to go into medicine, which my dad would totally agree with because he's a professor of medicine, and he's still trying to get me to do medicine to this day. Basically, she did go to medical school for a little bit, but decided, no, I want to do computer science. And that was a big commotion with her dad as well, so there's a common theme. But yeah, so I wanted to just give a warm welcome, everyone give a warm welcome to our Professor Dina Katabi.
Thank you very much. Congrats. Here. For you.
Can I use this mic?
Yep.
Okay. So hi, everyone. Thank you very, very much for everything. Thanks, Wendy. Thanks, Suja, and thanks, Bridget, and everyone. I'm really so thrilled to be here. So apart from the award that's very nice and the intro that's very nice, but also I got to see people that I haven't met, it turned out, in 17 years. And I guess we can all, it seems that we all MIT people, we look good despite that we are not that old, that young anymore. But okay, so I want to tell you a bit about what I do and tell you about wireless signals and how you can use them to see the world in a different way. And I'm going to start from Star Wars. Because I'm a big fan of Star Wars, and I'm guessing, given that this is a mostly nerd audience, so that many of you guys probably are also fans of Star Wars. So when I was young, which was unfortunately a long time ago, so I was really fascinated by this notion of the Force, this energy that connects all people and objects, and allows us to sense people, even if we cannot see them. And I remember actually even trying to sense the Force. I would be sitting at home, just focusing and trying to feel this force, this energy, and try, and didn't feel anything. But then, okay, I grew up. I recognized that this is not the right way to try to do something useful. So I became a scientist. And I later joined MIT as a student, graduated, became an MIT faculty. And the area of research that I worked on and still work on is wireless signals. Basically, these are things like Wi-Fi, cellular networks, how to make your Wi-Fi goes much faster, more reliable, the same thing for your cell phone and your data rate and stuff like that. And I did a lot of work in that domain. But then at some point in time, this force thing came back nagging. And I started thinking, OK, so these wireless signals that I work with, they have actually something more or less like the force. So if you just think about it, wireless signals travel through space, and they traverse walls and occlusions. And some of those signals actually reflect off the human body, because our bodies are full of water. And some of these minute reflections will come back. And just if I had a device that can capture these very minute reflections from people that I cannot see, then I can start actually feeling and sensing people that I cannot see. And that, to some extent, very much like the force. So I managed to convince my students to work on this idea. That wasn't easy. So we started working together and on this device that can capture wireless reflections from behind walls and occlusions. And I want to show you some of our early results. So here you see an office in CSAIL, in the computer science lab at MIT. This is our device. And we're going to put the device in the adjacent office behind the wall. And we want to use the wireless signal from the device as it traverses the wall, reflects off the body of this person to monitor how this person is moving. Now, you see on the side of the screen, you see the screen of the device. And you see a red dot there. This red dot is where the device thinks this person is standing right now. And as he walks, you can see the red dot tracking him. And actually, it's tracking him without any sensor on his body, just purely based on how his body is interacting with the electromagnetic waves. Yeah, for all practical reasons, he might be completely oblivious to being tracked. Yeah, when I showed this in a lecture to undergraduate students at MIT, I had a line of students. Everyone wanted to know whether it works in the dorms. OK, so let me just say at very high level, what is the technical idea? So this is very high level. So of course, the closest thing that you can think about is radar. So in radar, you transmit a wireless signal to the sky. It reflects off some airplane there and comes back to you. And this is how you can create this measurements of the airplanes in the sky. Now, but of course, it's not just radar, because if it were radar, we would just have this 50 years ago, or maybe more. So there are at least two key differences. There are more, but let me focus on these two key differences. So one thing is that you cannot blast power at somebody the same way as radar does. Don't do that, please, because you would fry him as if he were in a microwave. And particularly, don't do it to students. So this means that you are sending very low power wireless signals, something that as low power as your typical signal, Wi-Fi, or actually in our case, even 1,000 times lower power than Wi-Fi, which means that after it travels and goes through walls, these reflections are going to come back from a human body. They are very minute. So you have to be very sensitive, and you have to design your equipment, your signal, everything to be extremely sensitive. The second difference from radar is that unlike radar, which you are sending a signal to an empty sky mostly, so anything that reflects back, you know that it's most likely an airplane or something like that. Imagine like sending a signal in indoor setup. So there are so many things, and those things actually reflect wireless signals much more than the human body. So there are the ceiling, the walls, the floor, there is a screen here. There are other people around. And the hardest reflections actually are very complex multi-hop reflection. So the signal can come reflect off my body and then go reflect off Bridget and then reflect off the ceiling and off the wall. And you get a mass of reflections. And radio signals are very good at doing that. So you have to make sense out of all of that mess. So to do this, we were helped by two things. We were actually at the right time to try to address this problem. So on the one hand, radio technology have improved dramatically over the last decade or so. So we were able to design and build radios that are extremely sensitive so that they can capture these very, very weak signals that reflect back to us. The second thing is, of course, machine learning. So over the past few years, machine learning has seen a revolution of deep learning and new models that can understand very complex patterns. And what we were able to do is to design deep learning networks that are particularly focused on understanding electromagnetic waves. So we designed them, we trained them to understand electromagnetic waves and to eliminate some of the difficulty that you see applying a neural network to that domain. So you can think of the radios like the ear of our device, and the machine learning as the brain. And together, we got a very powerful device that can do a lot. So I showed you that we can track a person around, even through walls. So we can actually do even other things. So for example, we can track sleep. So this is another, this is particularly close to my heart because my sleep is a disaster, and tracking my sleep taught me a lot about, actually it told me that never try to track a physiological signal when actually you don't have it right, your physio. So at a high level, I'm sure you guys can kind of like think why we can track sleep, because I mean, we see the person as he walks to bed. We see when he stops tossing around in bed and when he steps out of bed. So we can track sleep based on something called actigraphy, so the motion-based tracking of sleep. But actually, so we started tracking sleep this way, but then we discovered that we can track sleep at much, much deeper level. Actually, we can track something that is related to the change in the brain waves as the person goes to sleep. So when we go to sleep, our brain waves change, and we enter different stages: awake, light sleep, deep sleep, and rapid eye movements, or REM. And these sleep stages are not just important for sleep disorders. They are, of course, very important if a person has sleep disorders. But they are also related to a variety of diseases. So for example, rapid eye movement, or REM, is very much associated with depression. When people that have depression tend to have disturbances in REM. And many of the drugs that people give to depressed people, SSRI, they oppress REM. So monitoring REM would be very interesting to understand depression and understand when people enter depression. Deep sleep, actually, the slow waves in our brain during deep sleep are very much associated and correlated with beta amyloid deposition in the brain in Alzheimer's disease. So being able to discover this can tell us a lot about beyond sleep disorders. So today, if you want to monitor sleep, and particularly sleep staging, what do? You send the person to a sleep lab like this. This is in the MGH sleep lab. And they put all of these electrodes on you. And they ask you to sleep like this. It's really not a happy experience. And many people can't sleep. Not surprisingly. But so what if somebody tells you that we can do the same thing for you, but in your bedroom without putting anything on your body or your head? So here you see our device on the wall. It transmits low-power wireless signal, receives those reflections, uses AI algorithm to analyze the reflection and spit out the sleep stages throughout the night. So this device, for example, would know when this person is dreaming, entering the REM stage. And the accuracy that we have is 80% in tracking sleep stages. Now, 80% actually is very high accuracy because when you go to the sleep lab, they take your EEG signal, and there is a clinician that sit there and for every 30 seconds try to decide whether you are in REM or you are in deep sleep. And if you take two different people, two different sleep technicians, the consistency among them is 83% on average. So now we are automating that process, so making the life of the technician much easier, but of course making the life of the person who has to go through this experience also much better. So what else can we monitor? We can also monitor breathing. So this person is sitting there, and we are monitoring his inhale-exhale motion. And what you see is nothing but the inhales, the exhales. We ask him to hold his breath, and you see the signal stay steady because he exhaled, he did not inhale. So, and again, we compared this with FDA-approved chest band from Philips that the person wears, and the accuracy is 97%, following the exact breathing pattern. So I want to zoom in on this signal. So this is the same signal that we got before, the breathing signal. These are the inhales, and these are the exhales. And you see that there are some blips on the signal. So those blips, they are actually not noise. They are his heartbeats. And you can see them beat by beat. Okay, so as you can see, with wireless signals, even through walls and occlusions, we can track many physiological metrics that are very hard to monitor today. And that got many people in the health industry very excited. So we started working with doctors, and doctors, of course, are always interested in knowing more about their patient, particularly about patients with chronic diseases. Because one of the things about chronic diseases, if you think about diseases like heart failure, pulmonary diseases like COPD, depression, stuff like that, these diseases, like problems that lead the person to end up in the hospital, they don't happen overnight. They actually are cumulative. So if you can monitor the patient continuously at home, you can detect the starting point. You can detect very early on that something is going off and intervene or have the doctor intervene before the patient ends up in the hospital. So today we have over 30 devices that are deployed with patients of different disease categories. So we are very excited working with doctors on pulmonary diseases such as COPD. We also have devices with people who have Parkinson's disease. We deployed with depression, also Alzheimer's disease. And I want to show you some of the results with the patients. So this is very illustrative result. This is from an assisted living scenario. So what you see here, you see the unit of the patient. So this guy lives in assisted living. You see a green box at the top. So this is our device. Actually, let me see whether I can use. I don't. Okay, so the green box here, this is our device. This red dot is the person. And there are two scenarios that I'm going to play. One is you see the patient movie, and the other one you see the nurse in the assisted living movie. And you will see that the nurse is much faster, but also the patient is not just slower. The patient also moves, has more wiggly trajectory than the nurse. So you see the nurse moving smoothly while the patient has wiggly and slow motion. So we take these trajectory and analyze them. And this is a particular patient who has Parkinson's disease. And what we are plotting here is the gait speed as a function of the hour in the day. And these results are average for about 3 weeks. So, so you see the x-axis goes from midnight to the midnight on the next day. And there are two graphs, one for the patient in blue and his spouse, which is a control case, in red. And if you look at the spouse, who's not a patient, she's normal, you can see that her gait throughout the day stays more or less along the same level. You see the patient, there is this dip around 5 a.m., and after 5 a.m., his gait starts improving. So you might be wondering what's going on here. And actually, this is exactly the time he takes his medications. So in Parkinson, actually, medications, like when the person takes medications, different patients may need different doses of medications. So if you can monitor exactly the reaction to the medication and when the medication wears off, then you can say, OK, this person needs higher dose, while this person needs lower dose. So I want to show you a bit more results from our patient population. So this result here is for sleep. And there are 6 patients. So bear with me. I know you are MIT graduates, so you shouldn't be scared of graphs. So, OK, so let's see how this graph works. So this is a clock. So the top is midnight and goes throughout the day. So 24 hours. And what you see, there are multiple concentric circles, and each circle is for 1 day. And this is 8-week experiment or 8-week pilot study. And I want you to start by just looking with me at this patient here. Let's look at this one. So this one, so he goes to sleep around 11 p.m. or 10:30 to 11 p.m. almost like most days. And then he sleeps all the way to about 6 a.m. And because all of the circle kind of like start around 11 and end around 6, he has reasonable sleep. Not great, he's a Parkinson patient, but look at the others. Right? Can you imagine? This is the sleep of somebody, and this is the sleep of another patient. Very fragmented sleep all over the map. They can sleep much more not feeling rested. And that's very important information to the doctor. And not only this, actually this information, we compared it with the standard instrument in Parkinson's disease, and which is like the questionnaire that they asked. Today they have a diary. They ask the patient, basically. And it is highly accurate in comparison to the standard instrument in Parkinson, but you don't have to like get the patient to do all of that diary and all of those reporting every day. This is breathing. So this guy has apnea. I showed you. I have to be up there for this to work? Slide. Oh, it went. Oh, I see. OK. I thought it's like weird technology. I have to be high.
That's how the wireless works.
Yeah. It's just like, OK, I don't know that. This doesn't go. Typically, my wireless goes through obstacles. OK, so I showed you that we can monitor people who have normal breathing. But this guy, actually, this is sleep apnea. And this person lives in assisted living, and the nurses wanted us to monitor him because he's not sleeping well. But then when we monitored him, we discovered that he has terrible breathing, sleep apnea. So you see the breathing kind of like normal, and then it stops. It stays at steady level. He's unable to breathe. And you see this pattern repeating. It actually repeats almost every 2 minutes. And for the vast majority of the night, he's like that. So no wonder that he's not able to sleep. So this is another patient. she's an Alzheimer's patient, but she has anxiety and depression. So what I'm going to show you is a video that shows that what she does is that she goes pacing back and forth, because she's very anxious. And actually, she wakes up at 4 a.m. and does this. She does it also sometimes during the day. So this red dot is the patient, and we are going to start the video. So now it's highlighting the time, and then it's going to start the video. So you will see her walk toward her bed. She's very slow. So it's moving slowly. It's going to speed up the video now, because otherwise we'll be here until tomorrow. So OK, so now it's like playing the video 25 times faster. So now she's on the bed. She will step back and leave very soon. So don't worry, she will come back. Okay. Here she is. She left. Now, almost every 2 minutes, she repeats this. She goes to the dining area, comes back to her bed, goes, come back, doing that. See, she's again here, and she will continue doing this. So what I'm plotting here for you are these pacing episodes. And every line is when she comes, and that area at the top is in her bed, and then she leaves. And that pacing episode, actually pacing is a metric in measuring anxiety. So I want to end by saying that actually I'm very excited about this, this new force. Like, I mean, when I started thinking about it, I was like, oh, this is like Star Wars, we're going to see through walls, and that's really, I'm still excited about that, and I'm very much excited about anything that's related to Star Wars. But I'm also excited about the ability of this wireless force to change healthcare as we know it. And one of the patients that we deployed with is my aunt. She has congestive heart disease. And before we deployed with her, she had an episode. She ended up in the hospital. And after that, we decided that we are going to deploy with her and have the doctor always watching that. And I'm sure many of you have parents or grandparents that you worry about. So I want you to imagine with me what would happen if every home of chronic disease patient has such a device so that will sit in the background, try to collect health metrics, and the person can just live their life normally. They don't need to wear sensors, to charge stuff, and you don't have to convince grandma that she needs the Apple Watch or anything like that. So they can just live their life normally, and there is this device watching their health, and if there is any health emergency, it will detect it before it occurs, alert the doctor so that they can intervene early. And that can dramatically actually reduce both the cost of the system and the hospitalization, but most importantly, of course, affects the life of many patients. So I'll stop here and take any questions. Thank you. Question?
Hi, my name is Dave Wang. I volunteer with the club, and thank you for this really fascinating talk. And this is very, amazing. The question I would have is, and I'm sure that this is something you're not your intent, but how would you prevent or make it more difficult for this to be used in a malicious way, or something like you could imagine like different countries' law enforcement or intelligence agencies using this in a not so beneficial manner?
Yeah, so that has multiple aspects. So one aspect is technologies to prevent people from using the device to monitor someone who doesn't want to be monitored. And the other hand are policies if people try to misuse the device, there will be some punishment. So let me tell you about the technology side. So because the device has a notion of space, like you saw that the device can control, or not control, but just understand space and how people are moving in space, one of the things that we do is that we ask you to prove to the device that you are not trying to monitor someone else. So the device will ask you to walk the space in a particular pattern, and if you fail like if it tells you take a step to the right and you don't do that, then you are trying to monitor somebody else. And the device would not allow you to monitor a space that you don't have access to. Now, of course, like all technologies, also you want to put certain policies so that people will be using it for good things as opposed to misuse. But you're completely right. One has to think about these issues very carefully. Yes?
It's working now. How can you get one, and how much does it cost?
I see. Choose it in the dorm. So you cannot get one immediately. Particularly, you have to prove to us that you're going to use it for good reasons. So, but basically, at this stage, it's not a product yet, so you cannot immediately get one. We do have a startup that's working on commercializing the device, so hopefully you will be able to get one soon. How much does it cost? So, as you know, in any type of electronics, it's really about how many of it you produce. So if you produce, there is nothing about this device that would make it significantly more expensive than your Wi-Fi box. So as long as it's produced at large quantities, it can have very low cost. At the beginning, of course, the quantities are smaller, so the cost will be larger. Yes?
Yeah, Dina, thank you very much for this. I'm fascinated by it. So you mentioned the collaboration with Philips as well. I'm wondering, have you thought about the integration of, there's still a role for wearables to play. Like the one thing that came to mind when you showed some of these gait patterns is, hey, if somebody fell, you know, Philips, for example, has one of the market-leading fall detection. Mm-hmm. Have you thought about how you'd integrate this with other kinds of wearables?
Yeah, so there are two things. One is the falls, and one is integrating with wearables. Yeah, so I'm not saying that wearables don't choose wearables, this is going to replace wearables. No, I'm saying that this is complementary to wearables. Of course, if you are going out, this is inside a particular environment, so you have your wearables. And it's, I think at the end is you want to fuse all signals that you can get. And depending on the person, some people may use wearables, some people may not use wearables. Some people may use wearables but not using them all the time. Like our cell phones, for example, we have them on us when we go out, but many of us, once we arrive home, we put them on the table and charge them. Women tend not to carry the phone as much because it's in the bag as opposed to be on the body. So what I'm saying is that you want to fuse all of the data that you have from all the sensors and combine it together. And that's where I think the future is going to be. For falls, actually, I didn't show it, but we can detect falls also very easily because falls are elevation, so we can detect the falls in the home.
Hi, so I'm curious, wow, this is loud. I don't even need the mic, so I'll speak a lot softer. How does this wireless signal affect your body biochemically? Because I'm very curious about this, especially since my mother always tells me, don't put your laptop on you because there are some wireless signals that will affect you. And so I'm always skeptical about what she says, and I don't know if there's any truth to that.
Yeah. So I think I would say follow your mom's order, just because that's what you should do always. Keeping parents happy is very important. But this device is transmitting at like orders of magnitude lower power than your Wi-Fi. So there is Wi-Fi here. We're still sitting here. We are all here. So if you are happy with Wi-Fi, then you should be happy with something that is 1,000 times less power. I mean, I don't, seriously, I don't think really any significant health issues, or at least none of the stuff that we know about the impact of wireless signals indicates that there would be any health issues with this particular level of power that we are using.
All right, so we're just going to do 2 more questions, so better make it count.
Hello, this is amazing. Earlier we heard the story of how you moved away from medicine, went into computer science, and now you're presenting how you're using the light side of the force for all these health benefits. So how does that feel, being able to contribute and,
I can tell you it makes my dad very happy. It's like he keeps telling me, I told you that you should be in medicine. It's like, yes, Dad. But I think it's actually very helpful indeed. As doctors don't think the same like engineers. There is like a very big gap of the way we try to understand a problem, think about a problem, and analyze a problem from how doctors perceive things. And I think although I only stayed 1 year in med school, but I come from a family that is all medical doctors. So understanding a bit the background and understanding even the basics. I mean, I come from Syria, so in Syria you study biology like in junior high, high school, like all the time. So having that understanding helped a lot. And what is really amazing is to see things that you would think as far as from each other as like our computer science and medicine coming together and being, no, actually can be part of one project, one type of research. So I find that fascinating, and the side perks is to make my family happy. And
All right,
Yeah.
one last question. Here
Yes.
you go. It better be good.
Thank you. So as of now, you're sending signals to the body, and then you're tracking the response. What about capturing signals which are coming out of the body? For example, breathing, it's exhaling from the body. There is no invasion into the body by radiation. Human beings transmit pheromones. It's the secret of chemistry. And there's also, maybe when my heart is beating faster, there is some sort of sound waves which are very hard to detect. So I'm not letting anything enter my body, but I'm giving signals out. So it's your challenge to target me without invading me. Is it possible? It's just a question.
So, so one thing is that wireless signals do not invade the bodies. I mean, they first of all stay mostly at the surface of the body at these current frequencies. And I think the question always, to the engineer at least, is that there is a particular signal that you are interested in measuring. Let's say, for example, breathing, or heartbeats. So that signal can be measured using a variety of metrics, but it's always sometimes like whatever the emission that comes from the body. So some of these emissions, like sound, maybe you can put something that is very sensitive microphone, but is there going to be so many other sounds around? Is this the best way to measure this particular property? So in many cases, you try to find a surrogate way of measuring something. This doesn't mean that you are invading the body, or it's really to magnify the signal that you are trying to capture. So when you are using wireless to measure breathing, for example, or the pulsing of your blood, it's not that you are putting that signal inside the body. It's really what you are doing is that you are allowing that pulsing to modulate a signal. And using modulated signal is easier to try to listen to the noise or the voice of the heartbeats and using the sound. But it's always interesting to try also to figure out, maybe there are many other things that we could measure about the body that we don't measure in using these wireless signals, and maybe there are different types of emissions of some sort that could be measured differently. Thank you.
All right.
Thanks. I just want you to get up. That's all I can.
Thank you.